how does that happen, right? Week 6 of Bio 303, which is ecology and evolution this summer, and also Bio 304, which is plant, animal, form, and function. And yeah, wow, we're really going fast through here. So this week, thanks for keeping up with, not keeping up with me, but basically it's been yeah, I'm slow getting things on there online. Sorry about that. And I really appreciate everybody being so understanding with me this summer, because I was a little late this week getting stuff up. It's been pretty crazy. So at any rate, so the next test, test 6, it'll be up very soon, and well, it'll be up today. And there's an extension on it until Wednesday to get it for full bonus points. And then then you can still turn it in by July 19th for full credit. And in fact, you can turn in chapters 6, 7, and 8 tests for full credit right up until July 19th. And test 8, of course, on that Friday by noon. But for this week, what I want to talk about is the 10-point test questions. I think they're kind of fun to talk about. And let me give you some background on them as well. And as I'm going along, you guys can live chat with me, and you can ask me any questions you want. So let me get settled here. Oh, let me see my microphone here. Good thing. All right. So Bio 303. This week's 10-point test question is it's a long one, actually. So you want to prepare it before you take the test. But basically, what I'm asking is a question that's about both ecology and evolution. And the question here is, what type of species interaction do you think is most important for driving the evolution or driving diversity? So think about it this way. We've got these different types of species interactions, and I'll pull up my PowerPoint here. And species interactions, things like symbiosis and competition. And competition and both symbiosis have for a long time been, especially competition, has been considered a really important driver of diversity. And when I threw in a whole bunch of natural history on competition, niche partitioning, how competition has led for the diversification of species to partition the niches. So I threw some examples in there of the shorebirds and how these shorebirds, like Elise sandpiper, western sandpiper, and plovers, and willets, and godwits. I know, weird names for birds. My dad is always making fun of those bird names. But those birds, they partition the habitat, and by partitioning the habitat more and more finely, you can get more and more diversity. And I also used some snail examples. It was pretty cool. I was in the Bahamas a few years ago, and I crawled up on this rock, and I looked down, and it was covered in snails, right? It was so cool. And it's like, within an area this big, there was like 4 species of snails. And I realized that each one, it was a different size class, and they were foraging in the rock different ways. So that's competition driving that evolution. And the other one is this really important for driving evolution is symbiosis. And there's lots of different types of symbiosis. And not everybody agrees on the exact definition of symbiosis. Some people say that the relationship has to be very tight, almost obligate. And in an obligate symbiotic relationship, both species, or at least one species, totally depends on the other. To survive, that would be obligate, all the way to, yeah, we depend on each other a little bit. We help each other out, like flowers and their pollinators are much more loose in their symbiotic relationships. They're not as tight. But symbiosis in terms of, let's see what we got here. Think about clownfish and sea anemones. That's a great example. They both help each other out. That's a mutualism. But you can have a clownfish in a fish tank, and you can have a sea anemone, and they don't have to be around each other to survive, but they do better when they're with each other. So that's one example of symbiosis. And then there's like, I've literally been on reefs and watched fish line up at a cleaning station. It's so cool to watch them. It's just like in Finding Dory or Finding Nemo, where the fish are lining up like a car wash, and then either the cleaner wrasse or the cleaner shrimp goes in there and cleans out their gills and picks off all the little parasites off their skin. That's also a symbiotic relationship, but it's not an obligate one as well. So the question for this week, coming back to it, is which one of these do you think is more important, competition or symbiosis in driving the evolution of diversity? And this is a 10-point question. So what I really want you to do is dive into like the different types of relationships, examples of symbiotic relationships, and examples of how those relationships are driving diversity. And I'll tell you that, as I just said earlier, competition for the longest time has been considered one of the most important drivers of diversity, and especially like the rise of predators, exploitative relationships. That's the third one, by the way, is the exploitative relationships where you're either herbivory, predation, and parasitism. And that was a major driver in the evolution of animal life like 550 million years ago at the beginning of the Cambrian. And for all you buffs out there, 542 million years ago. But that rise of the predators was definitely an important, those day-to-day interactions of avoiding predators or catching your prey were definitely a driver in evolution. So for this question, like I said, talk about either symbiosis, exploitative interactions, or a competition. Pick one. There's no right answer here. It's a hard one. It's an open-ended question. But what you've got to do is show me that you understand the exploitative relationships, the competition, and also symbiosis when you talk about it. And you've given lots of examples here, and that is important. Details. Show me details. If you haven't noticed, we like getting details on these answers, especially considering they're open book, open note. We're not really checking to see how you guys are answering these questions other than that you're answering them well. And just remember, don't cut and paste off Wikipedia, please. Okay, now, nobody's hit me up for a live chat yet, but let me move on to Bio 304 here. I'm going to pull up the PowerPoint. It's the PowerPoint number 24 on water and electrolyte balance. And this week, I didn't do all of chapter, I believe it's chapter 40. The book changes like every year. And if you use Campbell's book versus Freeman's book, it's so similar, but the chapters are all different. And I've gone back and forth between those. But this week, what you're going to talk about is how sharks, chondrichthyes, which includes sharks, skates, and rays, is elasmobranchs, which means like a plated gill. Elasmo is like a plated, and their gills look like plates. So that's the term elasmobranch, which includes all modern sharks, skates, and rays. And you want to talk about how they maintain homeostasis in water, because even though they are isoosmotic, which means they maintain the same osmolarity inside their body as outside, which means the water is going to be staying the same as the seawater with their bodies. So they do this by maintaining high levels of urea, but they also get rid of salts. That's why they're not isotonic, because they are excreting salt out their rectal gland. I know, that's kind of weird. When you look at a shark's butt, you'll never think of it out of there. And in this question, what I want you to be able to do is answer, how does a shark release or get sodium chloride out of them? And it's pretty complicated. And there's this really good slide diagram in the book called a model of shark excretion from the rectal gland. And what you'll want to talk about are sodium potassium pumps. And Bio 304, sodium potassium pumps are so important for animal form and function. Sodium potassium pumps work by pumping 3 sodium ions out of the cell and pumping 2 potassium ions into the cell. And that does 2 things. It creates an electrochemical gradient. The electrical part of the gradient is you have more positive charged ions on the outside than on the inside. So the outside of the cells become positively charged relative to the interior, which is also a membrane potential. Just like a battery, you can measure the potential of a battery at 1.5 volts. You can actually measure the difference in charge across a membrane as membrane potential. You actually measure it in millivolts. There is a millivolt potential across that membrane. So by pumping more sodium out than potassium in, you create a membrane potential. That is electrical gradient. Because you have more sodium on the outside and more potassium on the inside, you now have a chemical gradient. So you have an electrochemical gradient. That is important because that's primary transport. That is actually primary active transport. Next, you have a co-transporter. Co-transporters are secondary active transports. We got primary and secondary. Secondary active transporters are co-transporters, symports and uniports. What happens is once you start pumping sodium out of the epithelial cells, the one that are lining it, okay, what's going to happen is that you're going to pump the sodium out, and then it's going to come in down its concentration gradient through a symporter, and it's going to drag chloride ions and potassium ions into that epithelial cell of lining the membrane, right? Now, then you have a chloride channel, and that chloride channel is only on one side of the epithelium. It's on the outside, going out into the rectum of the shark, right, into his butt. And what's going to happen is that chloride, because you're doing secondary active transport, you're bringing it into that epithelial cell from like the fluids inside the shark, it's just going to diffuse through facilitated diffusion right outside the shark down its concentration gradient through that chloride channel. Potassium, there's a potassium channel, and what it's going to do is going to flow through another channel back into the interstitial fluid of the shark. Now, the way sodium gets out, sodium is going to actually diffuse literally between the cells, between the epithelial cells. So the epithelial cells will come together like this, and the sodium is going to diffuse right out of them like that. Because as you pump sodium out of the epithelial cell, you're concentrating it into that interstitial fluid, so it will diffuse out. And that's how sharks get rid of salt and also maintain osmotic balance. Okay, so make sure that when you answer that question, you know the difference between isotonic and isoosmotic. There is a difference. And like I said, make sure you have all the details of urea and how this salt excretion works. I want to hear all about, you know, the secondary active transport, primary active transport, and the chloride channels. And I'm going to tell you a little story. Renata, I saw where you just gave me a question right there. I'm going to answer that in 1 second or 1 minute. But I want to tell a funny story about shark meat. It happened when I was an undergraduate. And this guy I knew, he was trying to impress a lady. He fancied himself a good chef. Maybe he was, maybe he wasn't, I don't know. And he's like, I'm going to go get some shark meat from the store, and I'm going to cook it to impress this lady. And he opens up the package of shark meat. Don't ever eat shark meat. It's horrible. Unless you prepare it when you catch it. Just don't eat sharks. So anyway, he opens it up and he gets this whiff of pee smell. It smelled like pee. And he's like, oh my God. And he got on the phone and he's yelling at Publix, which is the equivalent of Smith's, and telling them that they're selling him rancid meat that smells like pee. Meanwhile, I'm laughing because I'm a biology major and I knew about this system that the shark actually has blood with urea in it. So the shark meat had urea and it smelled like pee. He didn't know that, and I was gonna tell him, but it was too fun kind of watching him get all mad and worked up about the shark meat tasting or smelling like pee. That's why you don't ever want to buy shark meat. There are way better fish to eat. For those of you in 304, you heard that I like mullet. Now, people from Texas will tell you don't eat mullet, but hey, it's more than just a fancy haircut. It's a delicacy where I'm from. Now, let me get back to some science here. Okay, so when calculating the proportion of biodiversity, do you divide the total abundance by the species abundance, or species abundance divided by the total? Okay. That looks like, I think what you're trying to do is calculate a Simpsons index of diversity. And the good news is here, on this test, you're not going to have any calculations of the Simpsons index of diversity. And basically, but what you do is you do sum up all of the populations. Do you divide the total abundance by the species abundance, or species abundance divided by the total? You have to actually look at the equation. I always did mine in an Excel spreadsheet and just typed in the equation and just calculated all of my Simpsons index of diversities. And right off the top of my head, I actually can't answer your question. I'll answer it to you on an email later, because I honestly haven't memorized the definition or the equation. I used to know it when I was doing this stuff lots of. But the thing that you need to know about diversity and how we measure diversity in characterizing a community is, the first one is a simple one: species richness. And every species, no matter how abundant or how common, each species counts 1. And I gave some examples of like birds. You might go down the Bosque del Apache and see, in the wintertime anyways, and find 10,000 snow geese. No, seriously, you can see like 10,000, 20,000. They've had 50,000 snow geese down there. And that would count 1. And there might be some really rare bird that shows up once every 5 years, and that would also count as 1. So when you do your species list for the day, no matter how common or how abundant a bird is, it's going to count as 1. So species richness tells you the total amount of diversity inside or wherever in your community, and it's weighted toward rare species. Okay, it's rated toward the rare species. Now, Simpsons index of diversity. What this diversity does, even though I can't remember exactly the formula for that, I should have looked that up before I came in here. But what a Simpsons index of diversity does says, well, you know what? There's another way we can think about diversity rather than just each species counting 1. Because, hey, I go out birding, I saw 20,000 snow geese, but I only had maybe 3 or 4 roadrunners. So how do we calculate that? How do we affect that? So 1 minus D is Simpson. Actually, Simpsons is just D, and D is the probability that if you're sampling, what is going to be the probability they're going to be the same. So 1 minus D is an index of diversity. So the idea is it goes from 0 to 1. 0 is like no diversity, and 1 minus D, and 1 is full diversity. And it's a function of the more diverse your ecosystem is, or the more diverse your community is, the more likely every time you sample a new animal, or if you're birding, the next bird you see, the more likely it is it'll be a different one. So if I'm out birding and every time I look at a bird, oh, there's a new bird. Like there's a white-breasted nuthatch. I turn and look, oh, there's a red-breasted nuthatch. Oh, there's a chickadee. Oh, there's a junco. Oh, there's a western bluebird. If I'm seeing a different bird every time I look, diversity would be high, and it would be close to 1 because I have no predictive ability of determining or knowing what my next animal is going to be that I see. So that would be high diversity. Low diversity is, let's say I go out birding and I'm like, there's another house sparrow, there's another house sparrow, there's another house sparrow, there's another. That approaches 0 if I only see house sparrows. Or if I'm looking out at a pond and I'm looking at 10,000 snow geese, which is kind of cool to see actually. If I look at every bird and it's just another snow goose, then the diversity would be very low. So it would approach 0, because if I saw 1 snow goose, then it would be most likely that my next bird would be another snow goose. It would be 0. So D is the exact opposite, right? D is flipped. It's the probability if I'm just looking at D, not 1 minus D. If I'm looking at D, then I have a high probability that my next bird will be a snow goose. So that'd be 1. So we like to think of it as a diversity index. So we do 1 minus D. Okay, I got a question. For countercurrent heat exchange, I understand that arteries form oxygenated blood from the body core and the veins transport cold blood back to the core. Wouldn't that make the body core cold? You're absolutely right. And so what happens is when animals like this get exposed to the cold like that, there's a couple of things they can do. Ducks can actually slow down the amount of blood flow to their feet, and that will reduce bringing in cold blood back into their body. The other thing they can also do is ramp up their metabolism. We do that. We actually can do that. We have hormones. I'm trying to remember. I think it's called thyroxine. As a hormone that can actually ramp up our metabolism. So in the wintertime, if you're ever been in the wintertime and it's stupidly cold outside and you go to someplace hot, you're suffering. Meanwhile, if you're at someplace really hot and you go someplace really cold, you feel much colder than you would because your metabolism has been acclimated to different different climates. So with this countercurrent heat exchange, yeah, it will make the body core cold, but they can either slow down that heat exchange or they can also ramp up their metabolism. And the other thing you can do is exercise. So some animals can be more active, and just being active generates body heat. And that's how the example with the leatherback sea turtle. For all you 303 people out there, you'll appreciate this one. Leatherback sea turtles are turtles. They're reptiles, right? We consider reptiles mostly ectothermic. You think of that as cold-blooded because they don't generate their own body heat. But these sea turtles, these leatherback sea turtles are like 6 feet long, and they weigh like 1,000 pounds. I can't remember exactly. They're like 1,000 pounds, but they're so big that when they swim, they generate body heat, and by generating that body heat, they can hold it in, and then they'll actually stick their fins up into the air, and that actually will warm them, and they'll bring in warm blood into their bodies. So that's how like a leatherback sea turtle. And I've actually seen marine mammals. I'm trying to remember if they were sea lions. They were in cold area and they were all sitting in the water with their fins up like that. I'm like, what the were all these animals doing? And my friend Blair Wolf's like, Tom, they're warming up. It's kind of current exchange. Come on, you should do this. Okay, that's basically all I have for this week. I just want to, like I said, thank everybody for your patience. And the summer has been really, really busy for all of us. It's been, you can probably hear my kid back there in the background. Dogs are trying to come into the door here. It's been really busy this summer. And also some of you have sent some very kind words over email with the messages. I really, really appreciate it. You know, one of the things of being online is I don't get to know you guys and you guys don't get to know me. And that's one of the tragedies of being fully online. But hey, we also get to work at our own pace. We don't wake up and go to school every day. And some of you don't even have to come to town at all. So this class is more accessible to more people. But I really do miss getting to interact with you guys. And for those of you asking questions and emailing me, it's been a really great experience. I've had some great interactions on email. And like I said, I cannot tell you how much that means to me to get those kind words from some of you. And also the examples for the podcast. Thank you so much for those suggestions on the podcast. I'm going to try to get one out. I've been so busy, but I'm going to try to get another podcast out because I really enjoy doing them. So thank you for all of those suggestions. And the blogs are up. The second blog is due next Wednesday for full credit. For the bonus points, if you get it done after that, it'll still count for full credit. Nothing's going to be considered late. Any questions? Go ahead and email me. I think I'm losing I think I may have lost my connection there. Go ahead and email me if you got any questions. There's something wrong with the test, let me know. It should be all right. If you have a question on if you have a question about one of the questions, just screenshot it, shoot it to me on Monday morning, and tell me what you're thinking and how you approach that question, and we can definitely talk about it. Okay, well, have a good weekend. Like I said, the test isn't due until Wednesday anyways, and it will be up later today. Have a good weekend. All right, bye-bye.